natural number. It's a special number like pi, right? But we use the letter E for the guy that invented it or found it. It's about equal to 2.718281828, blah blah blah. It doesn't repeat. It doesn't ever end. But it's a big, long, irrational number. We use the letter E for the guy that discovered it. His name was Leonard Euler. Euler, but even though it's spelled with a E and a U. There is a couple of different formulas for where this number came from, which we'll talk more about that in class. What we need to remember, though, is that E is equal to 2.718. It's a number like pi, and it acts like a variable like x, but we can simplify things just like before. If we have e squared times e to the fifth, since we see multiplication, we add those two powers together. And if we have something more complicated, maybe we need to simplify the denominator first, and that'd be 4e to the fourth, and then split it up, and 12 divided by 4 is 3, and then subtract those powers to get e to the fifth. If we need to evaluate a number, that means to plug it into our calculator and find out what number it is. How we would plug this into our calculator is just using the powers. There is an E button on your calculator. Now, you might have to look around to find it, but you should see it there. And then use the power key to the second power. What you should get when you type this in is about 7.389. So take a second on your calculator, make sure that you know how to do that. If we're going to graph it, this is an exponential function, so it's going to have that exponential shape. Since e is bigger than 1, it's going to be exponential growth. And we can use a little table to help us out. We wouldn't really have too many numbers in here to come up with the shape. But if we plug 0 in, anything to the 0 power is 1, and e to the first is about equal to 2.718. Now, any numbers that we plug in there, except for 0, is going to give us some messed up decimal. So these will probably give us a good idea of what the shape looks like. For instance, here we'll have the y-intercept at 1, and then 1, 2.7, about like that. Otherwise, we just use what we know about exponential growth to come up with a shape. Like exponential growth starts small, and then it gets big. So that's what our graph should look like. This thing has a horizontal asymptote at y equals 0. So now we can look at domain and range. We can plug any values in for x, so our domain is going to be all real numbers. The range, since our graph stays above this line, y equals 0, our range is going to be that y is greater than 0. If we need to shift it around, we shift it around. First of all, let's think about the parent graph that looks like this. And let's just shift these 2 points, the 0, 1 and the 1, 2.7, shift them around to see where our new graph is going to be. And when we look at our equation up here, this means that we're going to go negative 2 in the x direction, and this one means we'll go negative 3 in the y direction. So for this one, we do the opposite of the number that we see, and what's outside we do the same of the number that we see. So take our y-intercept right here and shift it 2 units to the left and 3 units down. So 2 units to the left and 3 units down. This point over here gets shifted 2 units to the left and 1, 2, 3 units down. And that will give us a nice shape of what this graph will look like. We're going to have a horizontal asymptote that got shifted 3 units down to y equals 3. So now we can identify the domain and range. Once again, just like all of our exponential growth functions, our domain is all real numbers. And our range, well, since our graph stays above this line, y equals 3, it's going to be y is greater than 3. The most common place where we use the number e is in the continuously compound interest formula. In class, I'll derive it, but for right now, I'll just give it to you. I always thought of it as the Appert Formula or the Appert Formula, just because obvious reasons. It says A-P-E-R-T. But what do all of these letters mean? A is the amount of money in an account at the end. P is the principal. That's the starting amount. E, of course, just like before, is 2.718. R is the interest rate, the annual interest rate, and T is time. And this time has to be measured in years. All right. So we just use the Appert formula, A equals P E to the RT, to help us solve problems that look like this. $4,000 is being deposited in an account to pay 6% annual interest, compounded continuously. How much is in the account after 2 years? Well, we just go ahead and grab that Appert formula, okay, and start plugging things in. If we want to know how much is in the account at the end, we start with our principal times E to the interest rate, 6%, so we use 0.06 times time. It's 2 years. So we go ahead and grab our calculator, 4,000 E to the 0.12, and let the calculator do all of that. One thing about this is for E, use the E button on your calculator. Don't just use 2.718. If you use the E button, it'll be much more accurate. Anyway, let the calculator do all of that, and you should end up with $4,509.98.99.